السلام عليكم.
وعليكم السلام ورحمة الله وبركاته. ازيك يا دكتور عمر؟ ايه الأخبار؟
الحمد لله تمام. ايه الاخبار يا جماعه؟
الحمد لله بخير. الحمد لله على سلامتك يا دكتور.
الله يسلمك يا شهد.
الحمد لله على
معلش
السلامة
بقى.
والسلام.
الله يسلمك يا عاصم. هو انت عاصم اللي انا اعرفه؟
عاصم انا. ايوه.
ازيك يا عاصم؟ انت فين يا عاصم؟ انت فين يا عاصم؟ محدش بيشوفك ليه يا عاصم؟
موجود والله. اخبار حضرتك ايه؟
الحمد لله تمام.
يا رب دايما.
الحمد لله. طيب يا جماعه نبتدي ان شاء الله ولا نستنى؟ انا مش شايف بصراحه العدد ايه، بس يعني احنا 3 minutes over، فممكن نبتدي ان شاء الله.
احنا 46 لحد دلوقتي، وأعتقد
م?
الناس هت continue يعني to sign in.
طيب تمام. طيب إن شاء الله let's start. بسم الله. طيب last time we talked about the um, the flow of the data from how we take it from the raw input through the different layers of the neural network, reaching to the output. And by and large, we said there's two phases. We can think of two phases when the data is flowing into the neural network. The first is the forward pass. This is what we were talking about last time, which was we take the raw input and then we put it through the network, which is basically a bunch of mathematical equations, which we described last time, and then reaching to the output. And then the second phase, which we haven't discussed yet, is the backward pass, which basically after we evaluate the output, we compare the output to the ground truth that we have in our training data. And from the difference between the output and the ground truth, we compute the loss function or the loss. In that case, the loss function is what calculates the difference. So the loss tells us how well or how bad the network is doing in terms of matching the output of the network to the ground truth that we find in the training examples. And for this, like when we're doing the backward propagation, the goal is to update the parameters, which are the weights and the biases, in order to minimize that loss. So last time we only talked about the linear operations that happen in the forward pass. So we talked about like what the dot product is, what is matrix multiplication, and how this relates to the computations that happen in the forward pass. And then we stopped at the point of saying um, everything that we compute as a linear combination of the inputs going into a node has to pass through something called an activation function, which the activation function introduces the nonlinearity to the model, basically. And then we stopped at this question of saying, why do we need to have, a nonlinear component to this, to the neural network? Can't we just achieve complexity and learn, different patterns in the data by using the different nodes? If every node has a different expression of the data and different set of weights, can't we just use multiple layers and multiple nodes to express this as still as a linear combination? And then I left you with this thought that if you stack more linear layers, you don't really increase the model's expressive power. The term expressive power when it comes to neural networks is a term that is usually used to describe how much complex behavior can the network accurately express. Meaning that if you have a function that goes like a zigzag pattern, for example, can the model actually describe this zigzag pattern and follow the data and fit a mathematical equation to describe this zigzag pattern, um, or not? So that this is what we mean by the model's expressive power. And the idea here, what I'm trying to say is, it doesn't matter how many linear layers you stack upon one another, eventually, it's gonna reduce to a single, basically a single, a single node, like as if you take all these layers, compress them down into a single node with just a linear transformation, a single linear transformation. Like you're doing a simple linear regression, which is kind of wasteful because you go through all this computation and eventually your mathematical solution is really just a linear equation. And to basically prove this, I quickly showed this, but we haven't really gone through it. But let's go through it together and kind of use the mathematical properties of matrices and try and see if we can actually convince ourselves that that's the case. So if we consider we have a very simple neural network with only two layers, um, um, so the first layer, H, the first hidden layer, is basically how we compute it if it's only linear. We take the inputs, which is X, and do a matrix multiplication with the set of weights. And then we add the bias. This is exactly what we talked about last time. But there's no activation function. Like last time when we described this, which says that this entire term goes into the alpha, the activation function. But here we're saying let's remove the activation function and just treat this as a completely linear system. So that would be like the first hidden layer, right? And then the output layer would just take as input the hidden layer itself. So the output from the hidden layer becomes the input to the output layer, which means that Y, in this case, this is the network output, is also going to be the matrix multiplication of H, now being the inputs for the output layer. Sorry, this can get confusing. Times the second set of weights, which are the weights that are connecting the hidden layer to the output. Okay, and then we also add the bias term. So if we just if we just take this equation, the equation here, y equals h times w2 plus b2, because we have the value of h, we can just substitute h for its value that we have here, which is x times w1 plus b1, right? And then remember last time we talked about the distributive properties of matrix multiplication. So if you have a term like this, we can distribute the W2 into this expression here. Remember we talked about left distribution and right distribution. This is an example of a right distribution where we're multiplying the left term, which is like two additive terms times a matrix, but we can also equate this exactly to being x times w1 times w2 plus b1 times w2. We haven't really done anything. We just distributed this matrix multiplication into this term here. And then you can kind of tell here that this term over here, like x times w1 times w2, w1 times w2 essentially can be reduced to a new matrix like w new, because again, because the multiplication is associative, meaning that we can either, like for this term, we can either multiply x by w1 and then take that product and multiply it by w2, or we can multiply w1 by w2 and then take the product of this and multiply it by x. So this essentially means that this term, x times w1 times w2, can then reduce to being x times w new. We call it w new, meaning that we only just took these two matrices of weights, multiplied them, and got like a new set of weights. And this now becomes the set of weights that we need to multiply by x to get to the y. The same idea applies here. Like we have the bias b1 times w2 plus b2. This term also reduces to a new bias term because eventually multiplying b1 by w2 is eventually gonna give us a scalar, and then the scalar adds to another scalar, so give us like a new value for the bias. So essentially, in doing this, all we need to really, think of is that instead of having two separate layers and every layer has its own weights and biases, if we just combine them together, we're gonna have just a new set of weights and biases, which do it exactly the same thing. They express y as just a linear combination of different values of x. So eventually this reduces to a single straight line, which is exactly the formula for a straight line, which is y equals mx plus b. In this case, m, the slope, is actually just a matrix of inputs, and the slope here, the b, is exactly the same as the bias. Does that make sense? Maybe the math would take a little bit to understand, but just following the regular, sorry, following the normal matrix multiplication rules, hopefully that would, make sense if you take some time and think about it. Shah, do you have a question?
انا مش فاهمة الجزئية اللي هي في الاخر دي اللي هي واي اللي هي بتاعت الدبليو نيو.
So can we think about what W is? Like when we say X times W1 or H times W2, what does the W represent?
دي مثلا زي كأننا بنجيب السلوب، هي
Yeah.
الايكويشن بتاعت السلوب.
Yes, so the weights, you can think of the weights as if you have, for example, a set of inputs. In that case, let's say there's 10 inputs, right? And then the set of weights is like having like a weighted sum of these inputs. So for example, if the weight connecting from your like if the weight connecting from your input to your hidden layer is, for example, 1, it means that you take the value of input, you multiply it by 1, meaning the value doesn't change. If you take the value of input, which is 1, multiplied by, let's say, 0.1, if your weight is 0.1, it means that you reduce the effect of this input in the, you reduce the effect of this input on the final output of the model. Like you weigh down the value of this input. So if we're doing this in a stepwise way, all we're doing really is that we're dividing this scaling part of the inputs to get to the outputs into two stages. And when we combine these two stages, W1 and W2, into a new matrix, W new, we're essentially combining these two steps into a single multiplication step. Does that make sense?
تمام، شكرا لحضرتك.
Okay, this might take a little bit to digest, but you can rewatch the recording and try to do the math in your head a little bit. But hopefully, hopefully maybe I made it easier for you to understand. All right, so I guess we agree now that we really need to introduce nonlinearity in order to get away from this linear trap that we can fall into by just ignoring or by just trying to combine systems of linear equations into a single one, because eventually all we're doing is learning a linear equation. So how do we introduce nonlinearity? So how we introduce nonlinearity is basically, as we said, every node, before it passes the output to the next layer, it passes the linear combination of inputs that it learned, which we also called pre-activation last time. Pre-activation because it's the linear combination that passes through the activation function. So this linear combination is called pre-activation, and after calculating the activations, after passing through the activation function, these are called the activations. And there is a lot of nonlinear functions that we can use. Can someone tell me just in an intuitive way what a nonlinear function means? Just very broadly, what do we mean when we say nonlinear function?
Function that doesn't necessarily produce a line, like in a very simple way.
Yes, exactly. So when you, for example, if you say y is a function of x, y is a nonlinear function of x, it means that when you plot y against x, the data is not really expressed by a straight line. It could be like an S-curve, it could be a parabole, it could be a hyperbole, it could be anything, but you can't really use a straight line to define the relationship between x and y. Very simple thing to think of is like quadratic functions, for example, or logarithmic functions, for example, right? So this is what we mean by a nonlinear function. It means that we cannot really express the relationship between the two terms using a straight line. So we're going to talk about these activation functions one by one, and talk about where they are used in different places in the network. The first one is pretty popular. It's called the sigmoid function. If you're interested in the math, I just put the formula here. Takes essentially the input x, the input that you provide to it, like which is x, and then puts it in this mathematical formula, which is 1 over 1 plus e to the power of negative x, and eventually you get an output that looks like this. So for a large values of x, the output of the function is essentially constrained between 0 and 1, which means that it doesn't matter how tiny of a value you give it, like minus whatever tiny value, it's gonna still give you something that is 0 or very close to 0. If you give it a very large number, very large positive number, it's still gonna give you something that is close to 1. Now, there's something that I wrote here that this function is nearly linear for the values of x that are around the 0. So like if you take that part here, hold on. If you take that part here, like let's say from -1 to 1, you can see that we can actually approximate this fairly well with a straight line, right? And in your intuition, is this a good thing or a bad thing? Any thoughts?
Good thing.
Hmm?
Good thing.
Good thing?
Yeah.
So it's a good thing that the nonlinear function that we're trying to use is linear at a big part of it. You think that's a good thing?
Yeah.
I
I
think
think
it's a bad thing.
it
Yeah,
make it
it's
more forward.
sorry, make it what?
More forward. So I have input and output, or I have a straight line that I can get some data from.
Yeah, but the entire idea of using an activation function is we're trying to introduce nonlinearity, right?
Yeah.
If a good part of your function, which is around the 0, is fairly linear, we're not really introducing any nonlinearity. So this is actually a bad thing because we would like to have a way to express the data aside from just having a linear output. Does that make sense?
Yeah.
Amr, do you have a question?
No, I was just going to comment on this. If you have a limited data set that's around these values, it can trick you into thinking it's a linear equation, but it's actually not.
Yeah. So and why do we actually even care about the values around the 0? Because as we progress, hopefully we get to something called batch normalization, and we're gonna talk about the fact that we can't really treat like raw values and pass them as they are into the network. In more cases than not, we do something called batch normalization to control a little bit for the um, uh, to control for the biases that can happen because of the different values in the input. So typically, most of the values that actually the network handles are going to be around this area, like maybe from maybe -2 to 2, or even like 1.5 to 5, depending on how we normalize the data. So actually, this range of input is really, really critical to the node to be able to handle properly. Another thing we were hopefully get to touch on it towards the end of today's session. When we're doing like the backward pass, the way we actually learn, the way we learn from like from the loss function, the way we learn how to change the parameters is actually dependent on the derivatives of the loss function with respect to the parameters. So for a linear equation, because this is linear, the derivative of the equation is actually constant because the slope is constant, which means that the model doesn't really learn well, or that doesn't really learn much um, from having like a linear segment in the activation function. If the gradient is 0, or the slope doesn't change, the slope's fixed, it means that the model can't really use this to update the parameters. This is not going to make sense now because we haven't explained the entire thing, but I'm just bringing this up, and then we're going to revisit it once we talk about gradient descent and whatnot. Okay? So the sigmoid function, or we also call it the logistic function because it was all used for like logistic regression all the time. If you've done any logistic regression, you will realize that this looks very familiar. Generally, we only use this activation function when we're passing the data from the last hidden layer to the output layer if we're interested in doing a binary classification. So for example, if we're designing a network, and in that network, we would like the network to predict a binary output. For example, the very popular example is training a network to highlight like spam emails, right? So the output of the model is usually, does this email represent a spam email or not? So it's like a 0 or 1 output. And this is where the sigmoid function or the logistic function really works well in the neural networks. Another variation of the logistic function is called the softmax function. The formula of the softmax function is quite different, but you can kind of tell that the final shape of the function looks fairly similar to the sigmoid function. The only difference between them is that this function can actually take multiple inputs. So instead of having, sorry, it can produce multiple outputs. So instead of having just a binary 1 and 0 classification, by the way, the sigmoid function only produces one output because this is essentially a probability. And if you have a single output that is, the total of the outputs of the probability is 1. If you have an output that is 0.8, the second has to be 0.2 because they need to add up to 1 eventually. So you don't actually need the two outputs. You just need a single one of them, and then you can compute the other one. The softmax function is able to actually output the probabilities of different outputs. And this is the case that we use when we'd like to do a multi-class classification. So for example, you have an image and you have 10 classes, and you would like to know if this image is representing like, let's say some animals, whether it's like a dog, a cat, a horse, what have you. So you have different classes, and then the softmax function can give a probability to each one of those classes. Why I'm saying probability? Because the outputs are constrained between 0 and 1, which is perfectly fit for, expressing the output as a probability. So when you have different scores between 0 and 1 for different classes, they will add up to 1, and then you can treat these values as being a probability that this output represents that class. And this is typically, the softmax function is typically used, as I said, again, in passing the output from hidden layer to the output layer when we're designing a network to do a multi-class classification. All right. The next one is the hyperbolic tangent function. This is classically was one of the used functions quite a lot because it also still looks very similar to the sigmoid shape with a major difference that it goes from -1 to 1 rather than from 0 to 1. Which means that this function is what we call symmetric because the average of this function is actually 0. And this becomes an important property when we're trying to pass the inputs through the hidden layers. So this wouldn't really be very useful in trying to summarize the output, in trying to summarize the network output through the output layer because there isn't really much inherent meaning to values that are between -1 and 1, for example. Unlike the sigmoid and the softmax, where the fact that the range of outputs are between 0 and 1, meaning that we can treat these outputs as being probabilities of classes. So the tanh is not really used that much anymore. And typically it was used within the hidden layers essentially to a little bit normalize or control the values within the hidden layer to avoid like mathematical explosion of values or something because we're restricting everything to be between -1 and 1. One of the very important functions is the ReLU function. ReLU stands for rectified linear unit functions. And now this function is strongly nonlinear. Even though it looks very linear and it's actually very simple, it's strongly nonlinear. And I will show you a detailed example of why or how this actually works and how can this kind of help the neural network to learn irregular patterns. What ReLU function essentially does is if it gets a negative input, it outputs 0, and if it gets a positive input, it outputs itself. So as you can see, like on this figure here, any negative input, like to the left of the x-axis, basically, any negative input here, it just returns 0. And then any positive value, it returns itself. So like 1 would return 1, like I guess that's 1 here. 2 would return 2. So this is not restricted like the other activation functions. It does not really restrict the output to a certain range, like 0 to 1 or -1 to 1. It zeroes out any negative values, and it returns the same value for a positive x. And the first time I've actually learned about the ReLU function, I'm like, this doesn't make any sense. Like we're trying to add nonlinearity and we're just returning the same value. And if it's negative, we're just returning 0. This really doesn't make any sense to me. It took me a lot of time to learn. And hopefully I will show you why this makes sense with a simple example. But the actually the strength of this function is the kink, what we call the kink it can introduce in different mathematical equations or in different functions. Because of this strong shift from 0 to positive, and the ability to actually kind of express any negative value as 0 and any positive value as itself, is exactly why it works well when we stack them the same way we stack the nodes in a neural network. This is one of the most commonly used functions in hidden layers. And again, I will show you an example why. Part of the problem, though, with the ReLU function, sorry, that's that part. One of the problems with the ReLU function is that when you have, for example, a network that outputs everything as negative values. Remember, there's really there is no inherent meaning to the output being a positive number or a negative number. Like it's not like a positive is a favorable thing and a negative is a bad thing. It's just a bunch of numbers and a bunch of multiplications and additions. So there isn't really anything bad when it comes to outputting a negative value. But ReLU makes it seem so. Why? Because when you output when the input to the activation function is a negative number, it outputs 0, right? So when the output of a function, or sorry, when the output of the node is a 0, it also means that when we go and do the back propagation, that this node doesn't really contribute anything to the learning process. Again, this is not going to be very clear now, but as we explain gradient descent a little bit today and then back propagation next time, this will make a little bit of sense. But the idea here is, think about it this way. If the output value of the node is 0, you're telling the network that this node is not really important. It's not really something to learn from, because whatever input you give it, it's just outputting 0. So eventually this becomes like a computational resource that you're using, but you're not really helping the model to learn anything. And this phenomenon here is called like the dying ReLU problem. The dying ReLU problem means that as you propagate your input through the network, if you happen to have some nodes that are always outputting negative values, and if you're using the ReLU function, you're always going to have 0 values there. So these nodes are essentially going to be dead. The model's not going to learn anything from them. They're just going to be there, and every time you do forward propagation, they're going to be there. You have to do the math, but when you do the back propagation to actually improve the parameters and improve the loss function, these nodes are completely useless. So all you're doing is just making like a computationally expensive operation by having lots of nodes, but they're not really helping the process in any way. So to solve this problem, a couple of modifications to the ReLU function have arisen. One of them is called the leaky ReLU function. Another one, which I haven't included here, is called the parametric ReLU function. And the idea is the same. They have a different implementation, but the idea is the same. Instead of taking your input and deciding that if it's negative, I'm just going to output 0, or if it's positive, I'm going to output itself. The only modification is that we just output, instead of outputting 0, we take that negative value and we multiply it by a very tiny number. In that case, it's called alpha. And in the case of the leaky ReLU, it's a fixed parameter that we select from the beginning. A popular value, for example, is 0.01. And essentially what you're doing here is that you're allowing for the small negative values to still contribute, to still have activation values that are not 0. And this way they can still contribute to their gradient as we're learning. So you're getting away from that 0 trap, that all negative functions are just, all negative inputs are leading to a 0 output, which makes it a dead neuron. In that case, we're just multiplying the negative number by a scaling factor to make it a very, very small number, but it's not 0, so it can still have a gradient. Does that make sense? I didn't include the parametric ReLU because it's very similar. Instead of having a fixed parameter, which is in that case, for example, one that's commonly used is 0.01, this parameter is actually learned in the network, meaning that every neuron can actually treat this parameter as something to learn, exactly like the weights, and every neuron actually gets their own alpha value. So it doesn't like in the leaky ReLU function, you set the alpha to the entire layer, and everyone gets the same thing. When it's a parametric ReLU, you can actually have a separate alpha function for every node. Same idea, different implementation, but the goal is the same. The goal is to allow the negative values to have a little bit of contribution and get away from this dying ReLU problem. Okay? Questions? Muhammad?
هو I have two questions
Mm.
actually. And please let me know if I'm a bit picky because I have seen before the ReLU function, but I don't know if the angle of the positive part make a difference or not. Or
It does not. This is only just the scale. Like the x-axis has a different scale than the y-axis. That's why it doesn't look like this.
mm-hmm,
Like normally when you see it in books, it's like this.
mm-hmm.
This is because the x-axis values have the same values as the y-axis values. This like if you look at this, like the
Yeah,
y-axis values, the one is actually here.
yeah, the concept it
So
looks like it will reflect the same one.
yes, so like if I do the same plot and I just change the y-axis, it's gonna be like this. It's gonna be like the similar ReLU function that you're used to.
And the second question is like how we choose or which one that would fit my data, like which activation function will fit my data, because sometimes also you mentioned like we enter with the raw data,
Mm-hmm.
and some models like PCA, for instance, I think we should normalize or scale first. While, for instance, in the RNA-seq, like DE-seq or lemma or whatever, we will have to enter with raw count data. So yeah,
So very very different things. Like when you think about, how the information flows in the neural network is very different from thinking about PCA or like RNA-seq and DE-seq and lemma. The PCA is actually a linear transformation. It's a completely linear operation. There is no nonlinearity to it. And the reason why you have to scale in PCA is because you're actually capturing a variation in your principal components. So if one of your features has a range of, 0 to 10,000, and another feature has a range of 0 to 10, meaning that one feature, let's say it's because you're talking about RNA, let's say it's a gene expression. Let's say this is one of the highly expressed genes in your cells. So there's like a range of expression in different cells between 0 and 1,000 as like a raw count values, for example. And then you have another gene that is normally has a very low baseline expression. So the lowest value is 0 and the highest value is 10. Now, when you go and capture the variation in the gene expression, you cannot really compare the variation within the scale of 0 to 10 to 0 to 1,000 on the same scale. This is not going to be fair because if you have one sample that has, a raw count expression of 800 and another that has a raw expression value of 900, there is a difference of 100 raw units there. This is not even possible when look at the second gene where when the maximum values are between 0 and 10. So the maximum expression difference you'll see is, let's say, from 8 to 9 or from 5 to 10. So the differences in terms of raw counts are 5 units versus 100 units. But the 5 units in the second gene actually represents doubling the counts because the entire expression is between 0 and 10. So if one cell or one sample has 5 counts and then a second sample has 10 counts, this is only a difference of 5 raw inputs, but this is actually doubling the expression. Whereas if you have the highly expressed gene and you go from 800 to 900, this is a difference of 100 counts, but this is only a 10% increase. So if you use them without scaling, this is going to be massively unreliable. This is going to be misleading. That's why you have to scale everything. You have to normalize everything so that when you express the differences, when you capture the variations in your principal components, you're really capturing the change relative to that feature that you're talking about. Does that make sense to you?
Yeah.
Okay. Um, the DSC and the other packages, the way the reason why you don't do any normalization is because the statistical model that they operate from is the negative binomial distribution. So the entire model is based to handle the negative binomial distribution. If you go and normalize your data, you're basically log transforming them and you're now kind of converting the distribution to become similar to a normal distribution. This is what something like Voom lemma, for example, does.
Yeah.
The Voom lemma does is essentially that uses the Voom to transform the data from being a negative binomial distribution to a normal distribution. And this way, the lemma package, which is actually really just for normal distributions, it's a linear package, can then operate, can then like the assumptions of the models, the assumptions on the data are valid that in that case. Whereas in the DSeq2 and HR, for example, they actually are designed to handle the negative binomial data. They're designed to handle the raw data, and they do a lot of tricks to also stabilize the variance. So like they have a lot of processes in place in order to get away from exactly what I was describing, which is called the variance stabilization. So if you go and read their papers, there's a lot of talk about how do we handle like the low expressed genes, how do we prevent the bias that come from the highly expressed genes. But this is all kind of baked into the model, and that's why you don't normalize. This is very different from what we're talking about here.
Okay.
Okay. So to answer your question now that we talked about the other parts, to answer your question here, usually, empirically, you would start by using, for example, something like ReLU or like a leaky ReLU, like a variation of the ReLU in your hidden layers. And then as you look through the metrics of learning, as you look through the performance of the model, as you're training the model, if you find that you have a lot of problems, if you find the model is not learning, the model is taking a lot of time to learn, for example, it's getting stuck somewhere. These are all things we're gonna explore. You start to experiment, or maybe I should use a different activation function. You start to do some troubleshooting, and then there's something called dropout that we're gonna talk about, and regularization, that can tell you, this is where you intentionally go and switch off some neurons and see how this affects the learning. So typically, you would start from something that people normally use or commonly use, and then if it gives you some problems, if you see that the network is not really learning, then you start to think about alternatives. And packages like PyTorch, for example, you will find that if you look up in Google just PyTorch activation functions, there's an entire web page of like tens of activation functions that are used, and people can like list examples of when this is useful, what kind of data this works for, what kind of data this doesn't work for. But massively, like by and large, the entire deep learning field, to talk about like the entire deep learning field, to generalize this, is very empirical in a way. Actually, a lot of things in deep learning just work because we know they work. We don't know exactly why they work.
The trial and error, I think.
Yes, exactly. But we can make like some sensible starting points. Like for example, you don't really want to use ReLU function in the output function. Like if you're interested in the binary classification, you know that you have to use the sigmoid in the output layer. If you do a multi-class classification, you have to use the softmax function, for example. There's a variation of ReLU also that is very nonlinear called the soft plus function, for example, which does very, very similar to what the ReLU does, except that it's kind of like very nonlinear in a way. So instead of having like this negative, instead of having a zero for every negative input and self for every positive output, it has like this curve function. It's called the soft plus function. You can look it up, but it does exactly a very similar job to what ReLU does. Um, and you will find that sometimes it doesn't really make that much of a difference when you change your activation function from something like ReLU to a soft plus, for example. Okay?
Mhm.
I know it's not a very deterministic answer, but this is the reality of deep learning.
I just thought about like if you want to make an inference from the height to have to know like the weight, no one have a negative weight and no one have a negative
Yeah,
length.
yeah,
So that's why, yeah.
yeah. I mean, eventually, you probably are not gonna have probably you're not gonna have negative values in your data set, and I don't imagine you're gonna have negative weights for any node. So I think this is kind of gonna be like implied with the data already. But yeah, you're right. Similar for like when gene expression counts and stuff, you're not really gonna have a negative value for a gene or something. Yeah. All right. So now let me actually give you like an example of how does ReLU actually, because as I mentioned, it's a seemingly very simple function to really introduce like a non-linearity in a way that can let us learn very complex patterns. Um, so this is kind of like how I visualize this to myself in order to understand what like this. And this is like a V shape, right? And can someone guess like a function that can use that we can use to describe this data? It's actually very simple.
Absolute function?
Exactly. This is really the absolute function. So y is just taking the value of x and rhetorical line here is really this is the function. This is y equals the absolute value of x, and these training points or my random points are just random values around these functions, right? And the key here is that there isn't really a single straight line that we can use to express this data. Like if you do a straight line like this is all going to be like, do it like a straight line like this is massively wrong as well. So there isn't a single straight line that you can use here to actually represent these data. So we need something more powerful. So how about we try and fit like a very simple neural network to this data? And the network is just going to be taking like a single input node, two hidden layers, one hidden layer with two nodes, and then a single output node, right? And then you have only two weights here, going from the input to this and going from the input to that. So W1 and W2. We're not going to do anything fancy, just setting the weight W1 just to +1 and the W2 to -1. And we're going to set the biases to 0. And for these weights and biases, we're also going to just have everything as 1. So essentially, there is no transformation going from the hidden layer to the output. By the way, this is also can be a use case. Sometimes if you're interested in the raw counts, oh, sorry, not the raw counts, the raw output, quote unquote raw, it's not really raw, but if you're interested in capturing the output of the last hidden layer in your output layer, you can use something called the identity function as your activation function. The identity function is just basically returning yourself. So f of x equals x, essentially, meaning that you, for example, have a network that has like 3 or 4 hidden layers, and you would like just to capture the value in the last hidden layer. So the last hidden layer just passes the value to the output layer without doing any transformation. Okay? Just saying. And this is quite common in regression problems. When you're interested in capturing like the continuous range from your hidden layers, you can use this. You can use the identity function as your activation function by in passing the data from the last hidden layer to the output layer. Back to this example. So we only have, as I said, a very simple network. We take a single input, x value, we pass it through 2 neurons in the hidden layer, and then we sum these two values and output a single y value, right? And we only have 2 weights. W1 is just itself, and then W2 is just flipping the sign of it, right? So now, the first neuron, when you pass all the data we have here, like all the data we have in the X, so like if we take the same X-axis values here, you see from -2 to 2 almost. If you take these same values and you pass them here, this is what the pre-activation looks like. We said that W1 is equal to 1, and this is the X value, and the bias is 0, right? So this is the pre-activation. This is before passing this into ReLU. When this, like when in the first neuron, when this gets passed like into the activation function, which is ReLU in that case, every negative value here, so all these values are basically just going to be 0, right? And then everything else is going to be kind of like itself. 1 is going to still remain as 1, 2 is going to remain as 2, and so on. This is the first neuron. So that's neuron number 1 in the hidden layer. So if we do the same process for neuron number 2, now the only difference here is the weight here that we're multiplying is -1. So again, we're taking the same x values here. Every x gets multiplied by -1, and then we add a bias of 0. So now this is the pre-activation. This is what neuron 2 does before passing this value to the ReLU function, and it outputs this straight line like this. Once this passes into the ReLU function, again, it outputs the same thing. For all negative values, they're all going to be 0, right? And for all positive values, we're talking about negative value of the y, but like the negative values of the y-axis, not the negative values of the input. Does that make sense? Because here it might be confusing that you're seeing a negative value here and you're still seeing a positive. When we say for the negative, it returns 0, it means when the y value is negative, then the ReLU function returns 0, which is this part here, which is like if you look here, it's this part here. This is where the y value is 0 is negative. That's why it's returning a 0 value here. Okay? So now you have one neuron that is outputting this and one neuron that is outputting that. When you combine these two curves, which is exactly what we're doing in the network, the output is summing these two nodes, right? So this is exactly what we're doing here. We're summing these two nodes. So for every x value, we're going to sum up the value from neuron 1 with the value of neuron 2. So neuron 1 is going to be 1 here, for example. Neuron 2 is going to be -2. It's going to be 0. -1, the same for this. We're going to take the value of neuron 1 and sum it with the value of neuron 2. Because everything here is 0, we're essentially just taking the value of the positive neuron. And you would do this, across the values of all the x, and then this is the final output. This is how the neural network learns to, when it gets a -2 as an input x, the output y is 1. When it gets a 2, the output is also 1, which is what? Which is exactly the y equals the absolute value of x. So using a very simple neural network and the ReLU function, we were able to introduce a break in the function, which is here. The slope was negative, it was going down, and then at the value of 0, we broke the line and we introduced a different linear range, which is going upwards now. Hopefully that makes sense. I kind of just had to create this example to myself in order to understand why is ReLU such a popular Asian function and how exactly can it help the neural network in understanding a nonlinear pattern. The idea is you do this like, hundreds or thousands of hidden layers, or sorry, nodes. You don't really do thousands of hidden layers. You do this in like hundreds of nodes. You can imagine like you can take any function, any irregular shape, and actually have like tiny bit of linear fractions, add them together to form like a very nonlinear function. And this is called the universal approximation theorem. I copied this exactly from Wikipedia. And what this exactly says is exactly what I'm saying, that the layers activation function, if it's non-polynomial, which is the case for a sigmoid function or ReLU function, not really using any polynomial equations, then this actually can act as an universal approximator in the sense that you can break up any nonlinear function into small segments of linear functions, and you can add them together eventually to make a nonlinear function. Yeah? Okay, let me show you one more example. This hopefully is How do I make it work? This should be a video. Wait. Hold on. There we go. So what you're looking at here is a neural network actually learning as it progresses. And you can see how the function is um, more towards the data as the network progresses. I'm gonna mention what epoch is, and then the other thing you can see here is how the loss is getting less as we progress, and how much nicer now the function is fitting through the data. So what this is essentially is there is a bunch of data points that come from like a very nonlinear function, like a sine wave, for example, right? And then we started this. Uh, so it starts as a random line here, and then as it progresses, it starts to fit its shape to the data. And you can see that the loss starts as a big number, and as this function fits the data points, the loss value gets lower and lower. This is exactly what happens in the training process. The word epoch here, the word epoch meaning every time the network passes through the entire data set once, every time the network sees the training data, the full training data once, this is called an epoch. And this is important because in bigger training data sets, in practicality, usually you would divide the data sets into different batches. So normally the network doesn't really train on the entire data at once. It trains at separate batches. But when these batches, like when the network has seen when it's seen the batches that make up all the data sets, we call this an epoch. So in here, we had to go through 208 different epochs for this network to learn how to model this data. And by the way, this network had 64 nodes in its hidden layer. So you can think of this as having 64 different spots where it can bend the line, essentially like we did with the V, having like a segment that goes down and a segment that goes up. It essentially did this, like it's going up, going up, going up, and then it's going down, down, down. And because it has 64 different nodes, every node can change the direction of the strand in a way. And you can see that when we do this, we can approximate basically the sine function using a bunch of using a bunch of straight lines. And then the other thing that we can take from here, because this is going to be a nice segue to what we're going to discuss next, is how this loss function changes over time. Like we can play it one more time. And you can see where the loss starts as this like function is like a straight line that is completely random. The loss is really a big number. And now as we move towards fitting the data, this then this loss value then becomes less and less as we progress. And I decided, like when I was doing this, I decided that I would like to stop when the loss value is less than 0.009. Had I, for example, told it to, you can tell it to stop, for example, when you've seen the data maybe for 200 epochs or 100, 150, or when the loss is like 0.00001 or something. Like you can do this however you want. This is the parameters that I picked, and this is the result that I ended up with. Any questions on this? Hopefully that makes sense. Is it all clear or is it very confusing and I lost you all? Muhammad.
Sorry again. So, but for setting the parameters of epoch, I understand, but for the loss, maybe that value wouldn't be reached any
Yeah.
soon.
Yes, yes. So like in this case, I know that the network is actually capable of achieving this. And if I like we're getting ahead of ourselves a little bit, but I'm gonna explain this in the future. So I ran this multiple times, and sometimes it would take 2,000 epochs to converge, and sometimes it would take 1,000. And in this case, for example, it took 200. This is because of the randomness in the way you start the process. And sometimes you're not able to achieve loss because you get stuck in a local minimum, and we're gonna talk about this now. So there is no guarantee. Typically, you don't really set a threshold for loss that you want to achieve a certain loss. More often than not, in practice, you train for a few epochs, and then you're actually plotting the loss against the epochs. And when you see that this curve flattens a little bit, meaning that with every epoch, the network is not really learning by much. The loss is not getting reduced by much. You know that you've saturated the network. So with your current architecture, with the way things are set up, the way you set it up, you're not going to be able to achieve lower loss. And you can kind of see this as you train the network. If you look at the relationship between the epochs and the loss, when you see that this curve is kind of saturated or plateauing, you know that this is it. This is the limit of this network. This was only meant to show you how the network essentially learns. We started from a bunch of data points. You saw that the initial random line was like a straight line, like this is really not fitting the data at all. And then as the network was training, you started to see that it was learning to follow the data until it eventually is fairly well representative of the data, I would say. And this was all done because of the ReLU function. Okay? So this is also a fairly simple network. It has 64 nodes in the hidden layer, nothing like fancy, just ReLU activation functions. And this is how powerful this is. This is how powerful you're able to create like irregular functions or nonlinear functions using bits of linear data. Any more questions, or shall we move forward? All right, I'll take this as no questions. So I guess so far, we can say that we've completed the forward pass, right? So in last session and today thus far, we have been discussing how the input moves forward in the network, right? So like starting from raw inputs, we talked about like the dot product between the inputs, the weights, and adding the biases, and then the activation functions, the different activation functions, where they're used, what do they do to the data. And then we saw an application of how an activation function can just break a linear line into different segments so that we can fit like functions to like very nonlinear data. So the next step, if you recall, like in the bigger picture of the network, the next step is we take this output that we just calculated from all the steps we discussed, and then we compare this with respect to the ground truth. So in the training examples, we give the network, whether these are regressions, so we're giving it like some features, and then these features correlate to a certain number, like the example we discussed, like surprising, for example, or it's a classification. So we give it like an image and a label attached to the image, and then the model outputs a prediction, and then it compares this prediction to the actual label on the data. And then this way of comparing your output to the ground truth is called the loss function. And from this, we calculate the loss, or it's sometimes also referred to as the cost. And then the process where the network actually learns, the process where, this process that you've seen here, going from this straight line to this curve that fits the data, is basically the modification of the parameters, which are the weights and the biases, to minimize that loss. And then the natural question to ask here is, how do we know which parameters to change? And by how much do we actually change them? This could be a very simple problem if we're dealing with something like linear regression. So you only have two parameters, you only have the slope and the intercept. If you would like to change the angle of the straight line, you change the slope. If you want to move it up and down in relation to the y-axis, then you um, change the y-intercept. But this becomes a much bigger problem if you're dealing with millions and billions of parameters. You don't really know which weights are important to the network because not every weight is important, not every node is important. And you would like to know which ones are the ones to change and by how much do I change them? Do I increase or decrease them? Do I increase them by a 1 unit or 10 units, or do I subtract them by 50 units? Or okay. So let's start from this. Like we've seen this last time or the time before, I can't remember, but this was essentially looking at the mean squared error, which is a classic loss function when you have a regression problem or a linear regression problem. And what you're seeing here is like a 3D plot of the slope being one parameter, the intercept being the other parameter, and this is the error. And you can see that because these are, there's two parameters here, you can see that there is like a plane, like a sheet of paper, you can imagine a plane of values. And this plane of values is concave in the way it's convex in the way it's represented here because there's like what you can imagine as being the like the high parts, like the top part here, and then it kind of slopes down into this area where you have lower loss, and then it goes back up here. So you can actually express the loss function, in that case, the mean squared error, as a function of these two parameters. And I'm just referring to the parameters as theta, which is very common in deep learning. And the idea is you would like to know if your loss is here. So if you pick random values for the slope and the intercept, and you calculate the mean squared error, which is loss, and you end up in this like red dot here, you would like to know, which direction do I move in order to reduce this loss? So do I move like this way? Do I move this way? Do I move that way? Or do I move this way? Obviously, in a setting, you're not really gonna have this entire landscape or entire loss plane computed for you. It's easy for us to visualize here, but normally when you're initializing a network, you just have some random values for the slope and the intercept, and then you can calculate the mean squared error or the loss for them. And then the next step for you or for the network to know is in which direction do I need to move along the slope and the intercept axes so that eventually I reduce this loss. And for this, we use something called the gradient. Turns out in calculus, there is a very powerful, concept called the derivative. And if you have a single variable, for example, for this equation here, you have x, you have a function f of x, which is x squared plus 2x plus 1. Not really going to go into math here, but the derivative of this equation, intuitively, what it means is that if you take a single point on this curve and you draw a tangent line to that point, when you calculate the slope of that line, which is delta y over delta x, this tells you the rate of change of this, or it tells you the change in this function, or the output of the function as you change x by a small amount. So this is what it says here, how much the function output changes as you make a tiny change to the input. So like if x moves from being 1.5, for example, to 1.6, how much does this change the output? This is what the derivative is meant to tell you, which in our case is what we're interested in. But before getting to demonstrating this, there's actually one thing we need to introduce, which is the gradient. So in this slide, we talked about the derivative. Derivative is when you have a single variable, and then you take the derivative of y over x, meaning, as I said, like the slope of the tangent that is to a single point that you're interested in which tells you how much the function changes as you make a time change to the input. What about when you have tons of parameters? When you have lots and lots of parameters, thousands and millions and billions of parameters, um, you extend the concept of derivatives to something called gradients. And the only difference between derivatives and gradients is that gradients are actually computed for a vector of values. So these are a multi-dimensional equivalent of the derivative. Like the gradient is a multi-dimensional equivalent of the derivative. And the way this works is you, instead of taking the derivative of y by x, here our y is the loss, you do the partial derivative of the loss with respect to every parameter. So like this is theta 1, theta 2, theta n. These actually represent the weights and the biases. So this gradient term here becomes a vector of numbers, and this vector of number has a single value for every parameter, and this value represents the partial derivative of the loss with respect to that single parameter that we're interested in. Is that clear? The only thing is we've taken this derivative and we just did it for every parameter in the network. Okay, I'm gonna move forward. So intuitively, what this means, or what this lets us know, classically in calculus, this gradient vector, when we calculate it, it actually points us to the direction of the steepened ascent in the loss function. So in a very basic calculus, every vector has two things to it. It has a direction and a magnitude, right? The magnitude is like the length of this vector, and then the direction is where it points, right? I think this is very basic. Hopefully everyone knows this. We kind of alluded to this when we were talking about the dot product and the geometric expression of the dot products, and how the vectors, the magnitudes of vectors can be calculated from two single vectors. Hopefully that's clear. But here, the idea that I would like to convey is this gradient vector in calculus, the way it classically is used is that this is a vector that points in the direction of the steepest ascent in the loss function. And because this is exactly the opposite of what we're trying to do, remember in our loss landscape, we are trying to not go towards the steepest ascent. We're trying to go in the opposite direction because we're trying to find the minimum point, like the point where this loss term is at its lowest point. So we can use the gradient from calculus and just reverse the sign of it, and this will actually take us to the direction where we move towards the minimum point. And this is exactly how gradients are used in training the networks. So we take to get to the bottom of the loss, or if we think about it like the bottom of the valley. This is usually pretty, like you will find this if you read any deep learning textbook. The loss is always thought of as like a valley of hills and a landscape of hills and valleys, and you would like to, if you're standing at like a hill, you would like to go to the bottom of the valley, and this is the analogy that is being given most of the time. So you compute the gradient vector, which it gives you the direction of the steepest ascent, and then you reverse the sign, so you take negative of this vector to go exactly in the opposite direction. So how this kind of works in deep learning is we start by calculating the gradient of the loss function with respect to the parameters. This is exactly what we said here. So like this is the gradient. We compute this vector of gradient. So this is a derivative of loss with respect to every parameter. And then from that gradient, we update the parameters by taking a small step in the direction of the negative gradient. So you don't take the magnitude of the gradient itself. In order to control this, you multiply this by a scaling factor, which we call the learning rate. And this number kind of controls how big of a step do you move. Like, for example, in here, when we move from this point, if we compute the gradient, we already know that this white arrow here is where is the direction that I would like to head um, in order to reach the local minimum. So this is the direction that I would like to take, right? But how far do I want to go? Do I want to go from here to there right away, or do I just go from here to there, or do I go from here to there? And this is what the learning rate is controlling. Um, in order for you to move, um, you we're going to talk about this next time, why this is important, because if you use the raw gradient, the vector, the raw value or the raw magnitude of the vector, it can become very unstable and can become very it can become very dependent on the actual numeric values in the network. And this is not a very stable solution when you're training the network. So thus we add this learning rate in order to basically scale the magnitude of this vector in a way that allow us to control the step size, like how big of a step do I want to take between on the error landscape between where I start from to where I end up in. And I mean, as you can imagine, like we showed the example of the sine wave function, this takes hundreds, sometimes thousands of epochs. And every time these parameters move by a little bit on this error landscape to minimize the loss. So in order to visualize this a little bit, I kind of drew these functions here. So this function, like the one you see in green, this is the same function that we started from, which is x squared plus 2x plus 1, which is this green line here. And then this function is actually the derivative of that function. So like when you compute now the derivative, I mean, now it's a single variable, so it's called derivative, but it's exactly the same thing as the gradient. It's just that because we have a single variable, we call it derivative. But it's the same idea. So if you compute the derivative of this function here, which is usually indicated by this apostrophe or dash, and then this is what you end up with. So the derivative of the function x squared plus 2x plus 1 is 2x plus 2, which is this purple line here. So if this is your function and you're trying to get your loss, remember, don't get confused. This is, in that case, x is your parameters. So this is these are in the network, for example, let's say it's one of your weights. And here, this is the loss. Why is the loss? So the goal here is to find the point where this loss is at its minimum point, right? This is what we're trying to achieve from this entire process, okay? So let's say you start randomly at this point here, right? So your weight is now set to -3. And you would like to know, how much do I change my weight? Let's not focus by how much. Where do I go? How do I change my weight? Do I go right or left if I would like this loss function to approach the minimum, to get to 0? And so what this tells you essentially is, because remember this equation here. Let's forget about learning rate now. This is a constant. Let's just set it to 1 or whatever now. For now, you have the new parameter, which is x in our case, equals the old minus the learning rate. Remember, the negative sign here is because we said the gradient classically tells you the steepest ascent, but we would like to go towards the direction of the steepest descent, right? So that's why we have the minus here. So because the derivative here is -4, the new value of x, so like your x new becomes your x old minus 4, right? So minus, in that case, -4 is your gradient or your derivative. So the x new, the new weight value, becomes your old x value plus 4, right? So you move in the direction that increases the x-axis, right? So now, by computing the derivative at this point, which represents a weight value, a parameter value, you know that I need to increase this value. I need to move this towards the right or increase it so that the loss moves more towards 0. Okay? And then the opposite is also true. Let's say you have a weight that is at this point, at this x equals 0.5 or something. You calculate the derivative of this point, and it's 0. So all you do is now, in order to know which direction to go, you calculate the x new, which is exactly your x old, which is like the 0.5, minus the value of this derivative, which is 3, right? So now you know that the new value is actually moving in the negative direction because it's subtracting 3 units from the old one, right? So if this was your 0.5, then you need to move towards the left in this direction so that you approach the minimum. Does that make sense? Okay.
أنا عندي سؤال معلش.
اتفضل.
هو لما يعني when we think of gradient descent, we're just thinking of how to like update or optimize our parameters, or is it more of, or are we trying to select specific parameters based on like how the loss function decreases or steeps or something?
What's the difference? Like you were saying, you said exactly the same thing. We're thinking about updating parameters and we're thinking about selecting parameters that minimize the loss. What's the difference between these two statements?
Because like later on when we do like feature selection or we're trying to select specific features, I'm just confused how because sometimes we can like do a machine learning model without gradient descent.
This has nothing to do with features. I haven't mentioned inputs, I haven't mentioned features, I haven't mentioned anything. All we're, focused on here is how the weights or how the parameters in general relate to the loss function of the model. We're only this is entirely like, remember, I just, when we plotted this, I just highlighted this, that the x value here, this is the actual parameters, like, or if we go back here to this slide, the entire thing we're talking about here is how, like, loss changes as a function of your parameters, weights and biases. We haven't really talked about features. We haven't talked about anything outside of the parameters themselves and how they relate to the loss.
Okay, thank you so
So
much.
so, so
Thank you.
can you tell me where the confusion is coming from? Like, why did you think of features in that case?
Like I don't know, it just feels like when we try to do like feature selection,
Mm-hmm.
um it felt that like gradient descent would kind of perform the same thing because it's like optimizing the parameter. But I think I just confused what parameter means and what a feature means.
Yes. So a feature is like, so in our case, for example, if we go back to the example of, the relationship between a house and its price, the feature is, in that case, is, for example, the house square footage. So how big a house is, or how many bedrooms it has, for example. This is a feature. And when you do feature selection, usually the question you're asking is, how is the feature important to the predictive power of my model, for example? So is this feature really changes the price of the house by much in an intuitive way, right? This is the feature selection part. What we're doing here is something different. You have a set of features, like, as we said, the square footage of the house and the number of bedrooms, for example. What we're trying to ask here is, what is the importance or what is the weight of each one of these features in deciding the price of the house? So is the we're not saying is the square footage a factor, but in and of itself, we're saying how much weight does the square footage of a house has in terms of deciding or predicting the price of the house. Do you see the difference between these two statements?
Yes, thank you so much. I think weight is the key word.
Yes.
Thank you. Yeah.
Okay. More questions? خلصنا على فكرة. We're gonna stop here because the next step is back propagation. I'm not gonna start back propagation today.
تمام، شكرا دكتور عمر. كان في فهد كان
We still have
عنده
10 more
سؤال.
minutes for questions. If anyone would like to ask questions.
كان فهد عايز يسأل على اللارج لانجوج مودلز. هو بيقول يعني بيعتمدوا برضو على الراليو ولا لا؟
I'm not keeping tabs on the chat, sorry. Uh, which section? Fahad, can you come off mute and ask your question? I can't see the chat for some reason. I don't know why. Hold on.
فهد is no longer Fahd is no longer here. That's why he's not
Okay.
responding.
طيب اوكي. في ناس كده ايه ده؟ الشات فيه حاجات كتير. Sorry, I wasn't keeping tabs on the chat, sorry. Um okay. Um which function is used in ChatGPT and other models? These are called transformers. These are different neural network architectures. Yes, it's like you can't row mountains, you do triangles. Yeah, everything is approximation. What is an epoch? As we said, an epoch is when the network goes through the entire data once. Each round is called epoch. Thank you for answering. No, the epoch is something we set at the beginning. ما شاء الله الناس بتجاوب اهو. برافو عليكم يا جماعة. Um, okay. If no one has any questions, hopefully today's session was clear. The gradient descent could be a little tricky to understand in an intuitive sense. But hopefully, like the last example with just showing the function and its derivative and how we can use these values to decide which direction to go, as in what the new weight is going to be in relation to the old weight looks like. Hopefully, this makes it a little bit clear. The details in the math and the calculus and as we discuss like backpropagation and we use a chain rule and whatnot can get complicated. I will try to not focus too much on the calculation, just mention enough if anyone is interested, but also not get too deep into it that we just get stuck in the math and lose the bigger picture. Hopefully, inshallah, it will all make sense. And I am hoping that after next time, after we discuss the back propagation, now that we will be kind of done with understanding the flow of, the information within the entire network, then we start to um, write some code, see how this works programmatically. And it's going to be so sad that everything we discussed over 3 or 4 lectures are going to be like a few lines of code in Python. Well, I guess it's also nice because it's very easy to implement, but it's kind of sad that we have to learn all that stuff to eventually implement it in a few lines of code. Mohammed, you have a question?
Yes, actually, this is the last question. I was about to ask about the same point of the math. So in the reality, do we have like, because I'm from a biological background, so do we have to really go deep in details of the derivative and this is stuff, or?
No, I would say you need to understand why we do something, like why the gradient is being done, what it allows us to do, and just a sense of like what I explained, and like in the derivative is just basically a way to at any point along a function kind of know what the change in the output is as you make a small change in X, because then you can kind of tell whether you want to move in the positive direction or negative direction. But it's not really, it's not really going to make any difference if you know how to compute a derivative of a function or a gradient of a function, or how to perform like back propagation in like using pen and paper and doing like the chain rule and everything. It's nice to know and to understand stuff, but if it becomes like prohibitive to understanding the math itself, it's not gonna prevent you from understanding how the network works.
Yeah, okay. Yeah, I just like I know that like just a gradient descent is just to reach the best parameter. So
Yeah, and just like maybe a little bit deeper than than this statement is just understanding how it does this, and hopefully with seeing the examples and the numbers and stuff, it makes sense that this is how a derivative value can tell you in which direction to move. Like the very simple example at the end, like if you have like um, a negative value, then you move in a positive direction. If you have a positive value, you move a negative direction because of this sign. Um, yeah.
thank you so much.
I have a quick question as well.
Mhm.
I
Mhm.
really enjoyed today's lecture, by the way. I have a question. When training a model and I find that training is not going the way I want to, there
Mhm.
a rule to when to switch from ReLU to 10H or the other way around or to other activation functions?
There's no rule. It's all very empirical, but like you usually do like some troubleshooting in like why is my model not learning? Is it getting stuck somewhere? Um, is um do you have enough input data? You can try and change the input data a little bit, see if there's something that is very noisy that is causing the or throwing off the model. Um, you can look into whether or not you have some batch normalization. Do you do any layer normalization? Do you do dropouts? Do you do regularization? There's a ton of things that we still haven't talked about that go into this. Remember, everything we're showing and discussing is like very simple functions visualized in 2D. In reality, like the loss landscape is like across hundreds of dimensions. So it's not even possible to plot this loss function or landscape uh, landscape looks like. But if your model is not learning, there's a ton of things to check before thinking about changing the activation function.
Okay, thank you very much.
No problem. Again, sorry that some of these answers are not very deterministic in saying this is what you should do, but this is a reality of the deep learning field. There's actually one slide that I put here that I actually decided to not show because it's silly, but maybe I can show it. Hold on. Do you still see my screen? Oh yeah, you do.
Yeah.
Uh, yeah, this slide here. So like, why do deep learning models learn? No one really knows why. Deep learning systems are so complicated, that's why they learn patterns so well. And then deep learning systems are so complex due to their non-linearity, that's why they learn. Or none of this is true, or all of this is true. What do you guys think?
I think nobody really knows why.
What's
I
that?
think none of the above.
It's actually all of the above. Yeah.
Okay.
So there is a very like I know people who've done PhDs in trying to understand why a network learns. This is their actual question. Why is it that the network actually learns? Why is it that when I set it up this way, it's able to predict this correctly? It doesn't make sense. Like for me, again, like ReLU function, like it's knowing that this is the most commonly used function, and all it does is that, yeah, black box models, exactly. All it does is that it just takes a negative value, switches it to zero, and takes a positive value, outputs itself. and then you tell me this is the most powerful way of learning nonlinear patterns. This for me was like, no, that doesn't make any sense. So, and as things get more complex and, with more, advanced architectures and more complex architectures, there's a lot of black boxes in deep learning, and we don't fully understand. Like one of the major things in deep learning when we're training the network, something called the dropout. Um, and dropouts is essentially meaning that you take, like, when you're training the network, you take some neurons and you just switch them off. Like you completely get rid of them. And we're not talking about something that is 10% or 5%. We're talking about 50% of the network. So you're designing this network with like 2 or 3 hidden layers and like 1,000 neurons per, or 1,000 nodes per hidden layer. And then you just intentionally choose to shut down 50% of these nodes. The intention behind is you don't want the network to rely too much on a single node. Like you have like this single node that learns a lot about the pattern, and then other nodes don't really learn much. So you do this in order to kind of spread the learning across the entire network. But still, for me, this is crazy. Like 50% of the network is being dropped out with every, with every epoch or something. Um, and people have done experiments and published papers on like how the networks perform with and without dropouts and with different rates and different percentages. And it's just crazy. Like no one has a true answer why dropouts really work. And this extends to many parts. There's a lot of empirical knowledge here, more than we able to reason. Um, but I guess at the end of the day, that's why having like a quantitative way, like a loss function, and having like, that's why people do like simulated data. Like, like, for example, sometimes you can't get ground truth. Like, for example, if you're dealing with like genetic data or RNA data or something, you can't really take ground truth that this is really what a CD8, T cell gene expression profile looks like, or this is what an exhausted T cell looks like, or this is what, I don't know, like a lung epithelial cell looks like, or you can't really like take that. You can take a cell and sequence it, but the sequencing is inherently noisy. It's gonna vary from batch to batch, from technology to technology, from technician to technician, from like the way you just set up your analysis, the way you filter genes. Like it's never like a way to like get like ground truth of how something looks like. That's why people like do like simulated data sets and use this as like, because this is data I made myself. I know it's supposed to look this way, and that's how I would test my model if it's able to do it or not. Um, so it can be frustrating at times working in the field because of how like seemingly random and unknown things are, but at the same time it's kind of fun because at the end of the day, if it works, no one's gonna tell you why does it work. The answer is I don't know, much like, a lot of things we don't know. So just, get off my back. Yeah, sorry, I'm ranting for a lot, and I realize we're over time. So thanks everyone for today's session. Hopefully it was useful. Inshallah, next time we're gonna continue like revisit gradient descent. This time was just an introduction. Next time we're gonna go a little bit deeper into it and then introduce backpropagation as well. It's also gonna be a slightly heavy session, but then afterwards, hopefully we're gonna get to code a little bit and build some networks in PyTorch and see how they worked. And then start to explore some of the architectures, inshallah. Assalamu alaikum.